So I started the discussion of large n limits with these so-called vectorial theories, where you have the so-called ON vector model, just described by ON invariant phi-4 theory with this phi I squared Lagrangian, and I mentioned. Okay. Yeah, so I mentioned that the ON vector model is solvable in the limit where n is sent to infinity while keeping Gn fixed. And the particularly interesting range is where basically we have d less than 4, so that the theory flows to some interacting fixed point. And I also wanted to mention the following thing. I talked about the 4 minus epsilon expansion, right, last time. So there is this golden range where these theories are particularly interesting. This is the range of dimension in D. So we have 2 here and 4 here. So we have basically fixed points. They're often called Wilson-Fisher fixed points, but I'm not sure it's the right attribution. Fixed points with ON symmetry. ON symmetry. And they're particularly interesting in this range D less than 2, less than 4. I already mentioned that here we have the 4 minus epsilon expansion from just this renormalizable field theory. And then I also mentioned the 2 plus epsilon expansion here. And this is actually obtained from something called the nonlinear sigma model. So this nonlinear ON model basically can be written in the following way. You can write the path integral z, which is the integral over this ON vector field, right? And also you have this auxiliary variable sigma, and now e to the minus 1 over 2t. T is the coupling constant, and here we have some scale m to the power d minus 2 ddx d mu n dot d mu n. And then you also need the constraint. So you have the constraint here that this is the nonlinear constraint, that n squared is equal to 1. Obviously, this constraint was not imposed in this field theory from the previous slide, but now we want to impose it. This can be done, for example, by treating sigma as a Lagrange multiplier. And then we have basically this enforces the delta function constraint point by point, right? So this is a pointwise constraint, right? Okay, so this is another famous model, famous enough that it is in Peskin and Schroeder. Also, you can read about the large n expansion for this model. I mean, it's very similar to the handling of the model that I'm about to show in the large n limit, but this can also be handled at small n, and in particular, so Polyakov studied the O3 model and found that it's asymptotically free in 2 dimensions, right? So this gives an asymptotic freedom, freedom in d equal 2, in d equal 2. And then another, this was before my time, of course, but another important paper I know about is by Brezin and Zinjustin, who actually developed they took the full ON model and developed the 2 plus epsilon expansion for it. Okay, and their result was basically the following for arbitrary n. They found that that the beta function or RG flow equation for this parameter t, which is dimensionless, is dt d log of the scale is equal to epsilon times t minus n minus 2 t squared divided by 2 pi plus something of order t cubed. And again, I believe this also is reviewed in Peskin and Schroeder. And then the whole point is that so this theory is actually not renormalizable in above 2 dimensions, right? So nowadays people talk a lot about non-renormalizable theories. Okay, so if you plot this beta function in this case, if you plot the beta function, it basically looks like this for small epsilon, right? So what you find in this case is that the flow lines sort of emanate like this if you flow towards the IR. So you find the UV stable fixed point, which is also weakly coupled because t is small. You find that this t star is equal to 2 pi epsilon divided by n minus 2 minus, plus order epsilon squared. Okay, so all of this makes sense only for n equals 3 and higher. So O3 is the first example of this asymptotically free theory, but they continue to be asymptotically free for n greater or equal to 3. So they study this case of n greater than or equal to 3. And this...
Can I ask?
Yes?
So what's that t? I missed that point. What does t stand?
T is just a coupling constant in this model. Yeah, it's just the overall parameter, just like you write like 1 over g squared in Young-Mills theory.
I see.
You'd simply take it outside of the nonlinear Lagrangian. But you can also expand and in some, you can solve this constraint and expand, and then you find that T measures the interaction strength between the fluctuations of this n field. Okay? It's yes?
What are the systems described by models with n greater than 3 that people often describe?
If physical systems, yeah, I think this does have applications to the O3 is of course the primary one because it's the Heisenberg model which kind of describes 3-dimensional spins. I think there are applications to condensed matter systems for n bigger than 3. I can't promise large n, but for example, O4 is a very common group. Like you sometimes have a, because O4 is like SU2 cross SU2, so you can have some degrees of freedom which are SU2 cross SU2. So it's a widely studied model, and the whole point is that this model is actually just like this 5-4 model that I discussed yesterday, is not scale invariant in 4 dimensions, right? Because of this non-zero beta function. Similarly, this model is actually not scale invariant in 2 dimensions because of this flow dt d log m equation. So you have to go to 2 plus epsilon, basically. And this actually allows you to study 2 plus epsilon expansions of things like, so can derive, so using this you can derive 2 plus epsilon expansions of things I discussed yesterday, like delta phi, this ON vector field, or delta phi squared, which is related to the so-called new critical exponent, like a critical exponent. So there are various, when you approach the second order phase transitions, there are various critical exponents that are related to exact scaling dimensions of various operators. And basically, you can then just do what I said yesterday. For example, for the Salon model, you can start plotting. So this is d is equal to 2, and then the dimension. So the dimension of n for n equal to 3 is just 0. So it goes to 0 here. Okay, and then it's 1 in 4 dimensions. So this is 2, this is 4, and you can do some kind of extrapolation. You basically know the results here, you know the results here. This is 1, this is 0, and then you can try to extrapolate to 3 dimensions here. So this gives you basically additional control. If you don't know this, it's a very classic result about just scalar field theories that are worth learning, and a lot of literature is available on them. So this just, I should say that these 2 plus epsilon expansions in terms of the behavior of coefficients, they're not as well behaved as 4 minus epsilon, but they're still very helpful because you're nailing down information sort of on the other end. Okay, so now, so I started discussing this 1 over n expansion. Let me just briefly show you some result. Okay, so now let me talk about the 1 over n expansion using this Hubbard-Stratonovich auxiliary field sigma. As I mentioned last time, you can basically write down the equation using this auxiliary variable sigma, then integrate out phi, and then you get, for example, in the one loop approximation, you get this exact propagator for sigma p. This is what you call the induced propagator, right? I already showed some results along those lines, but I can, if you want, I can. So essentially what we're doing here when we're computing the effective action for sigma is we're just evaluating this diagram, right? If this is the sigma line, so initially sigma is not dynamical, but then you're doing this loop of phi fields, and this diagram is rather simple, right? So in momentum space, we just have to do the integral, which is integral d dq divided by 2 pi to the d. 1 over q squared and p minus q squared, right? This is sigma of p. This is sigma minus p. Okay, when you do this integral, you get this expression, which I already wrote down. Maybe I'll write down again. Okay, you get minus pi squared to the power d over 2 minus 2 divided by some d-dependent stuff, which I already wrote down, some f of d, which it's actually in this paper by Fei, Giombi, and me, so you can read it. But the crucial thing is that if you go to low p region and d less than 4, this dominates over this constant, right? There is some additional constant, which is initially there was this 1 over g, and you can just forget about this at low momenta, and you get this exact propagator. Then you simply invert this, right? You invert this, and you get this expression here, right? This is the propagator for sigma field. Make sense? It's a beautiful manipulation. It's actually very simple to explain. How initially a field that is non-dynamical can acquire induced dynamics through coupling to other fields. And then if you actually Fourier transform this function, you get some 1 over x to the 4, right? 1 over x to the 4 just tells us that the leading dimension of this sigma field is 2, right? Whenever I have some 2 operators, so you know this golden relation, O of x of y is equal to some normalization factor, let's call it constant, divided by x minus y to the power 2 delta O. This is the basic relation about any scale invariant theory, right? This scaling dimension of operator O enters with the power 2 here. So you see immediately that delta of this sigma is equal to 2 plus some order 1 over n corrections, right? And this is the leading large n result, okay? Yeah, you can, as I mentioned, you can, in fact, I will list the archive number of the paper where this is reviewed. All right, so then let's look at yes, then you can use this sigma propagator and attach it to use this sigma propagator to develop 1 over n expansion for various physical observables, these delta sub phi squared. And in particular, this dimension, delta sub phi, the bare dimension is just d over 2 minus 1. So in the leading large n limit, the field just has free dimension, right? This is the engineering dimension of the phi field. And eta 1, the 1 over n correction, just comes from attaching the sigma propagator, right? So you basically want to take this phi field and attach the sigma propagator, and this gives you a factor 1 over n. And the integral that you need to do, this is the sigma propagator, right? This is the sigma propagator, and this is just the propagator of the phi field. And here we had to add some regulator and then eventually send it to 0. When you perform this integral, you find the following expression for eta 1 in d dimensions, right? You get this following function. I'll show you a plot of this in a second. And you can then, for example, take this eta 1, and then you can expand it, for example, near 4 dimensions or near 2 dimensions, and compare with the results of these perturbative calculations. So one perturbative calculation near 2 dimensions is the sigma model one, and the other one is from renormalized perturbation theory of just 5-4 theory. And you can check this result against these 2 results. Okay, and one thing that you can immediately do with this is that this formula doesn't just work perturbatively in D. You can apply it in D equal to 3. And so in D equal 3, then you can do more complicated calculations. Actually, so this result so far, I computed this here. Then people went to this order and even to the 1 over n cube order, which is a very complicated calculation carried out by Vasilyev and collaborators in the 90s, I believe. And then S is just this sigma field. That's just the ON invariant field. T is the traceless symmetric tensor operator. So T is It's just to explain notation here. There is an operator t, which is just phi I, phi j, right, minus 1 over n delta ij times phi squared. And for each of them, you can develop these 1 over n expansions. And these are a summary of some of the results. And now this is the new stuff about from Conformal Bootstrap. Yeah, I won't try to really explain what Conformal Bootstrap is. It's a totally different scheme of things where you essentially, instead of doing these concrete perturbative calculations or 1 over n calculations, you basically use some general properties of 4-point functions. Like you essentially have some 4-point function like O, 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 O with some coordinates x1, x4. And you use the fact that it can be expressed in 2 ways. You can either express it in this channel, say x1, x2, or you can express it in this channel. So it's a kind of crossing symmetry relation. And then there is some very nice mathematics about expanding this around a particular point that was pioneered by Rычkov around 11 years ago. And you get very interesting results. They obtain some exclusion plots in this delta phi delta s parameter plots. So for example, for the simplest case, n equal 1, the Ising model, you see that very early on they already obtained this kink at 0.518. And then for O2, so this is actually an old paper. By now this has improved a lot, but this is the first paper which also did the higher n. In particular, they did O6 here, O10, O20, and so on. And what these crosses are is the results from the 1 over n expansion that I just showed. So in particular there, yeah, so they basically took these things, evaluated them for n equal to 10, 11, 12, and plotted delta phi versus delta s. And you see that the positions of these bootstrap values are extremely close to 1 over n perturbation theory. The 1 over n perturbation theory, you see that at large n, you approach this dimension of s approaches 2, and the other dimension approaches 1/2. So you're going to be accumulating near here. And here you see very good agreement with these large n values. So it's, I mean, one can also try Monte Carlo, but I think it's rather difficult for large n, although I'm not an expert. But you don't want to be Monte Carloing 100-dimensional spin or something like that. But actually here the stuff becomes much easier. Like n is just a parameter in this bootstrap, so they can do it for any n. Yes?
What are the blue dots? With the one with the arrow bars?
Oh, yeah, these are, the error bars I think is just, I think these are just uncertainties in the 1 over n. They're estimating the error in the 1. Yeah, this is whole thing is the 1 over n, and they're estimating the error of the 1 over n expansion. Because as I said, like for 6 or 5, this 1 over n expansion is not so good. So you get like larger error bars. But for 10, it's already considered pretty reliable.
And the dashed line?
Oh, the dashed line, yeah, it's their best. It's the 1 over n expansion. Like just extrapolating the 1 over n expansion from large. So you see here it starts to deviate. But basically 1 over n expansion, it's very hard to extrapolate below, say, 8 or 7. And you see here there is deviation, but starting 10, it agrees extremely well with these bootstrap determinations.
And why do you have curves from the bootstrap as a
Oh, the bootstrap it's like an exclusion curve in the parameter space, like everything. Yeah, and what they noticed early on is that this exclusion curve has a kink at the special value, which is very close to the known operator dimension. So by now, these kinks have been promoted to little islands. So these little islands, what they now know, at least for low n, is never mind these plots. They will just show you a tiny little island around these points, and you know that the scaling dimensions must be within this island.
Yesterday you called the various resummation techniques that are tried, you call them a mix of science and art?
No, this is rigor. This is actually science, I think. Or yeah, because they have, to quote Ryczkow, he says, they have basically some kind of semi-definite programming. I don't work on this stuff, but I just listen to talks. And they have an oracle that says either no or maybe. Okay. So when you imagine that there is a little island around this point, everything outside it is no, but there may be something in here, and this maybe region is really tiny and includes what we know to be the Ising model. That was actually a very, very big result that they obtained a few years ago. And then similarly for O2 and O3 models they have. Then I think it gets harder for larger n, this approach, because they need to keep track of many more. They really have a multi-parameter space. For the Ising model, it's just two parameters, this delta phi squared and delta phi, and everything works beautifully. But for higher dimensions, it gets much more complicated. But basically, it's all pointing to a very successful program, and also goodness of the 1/n expansion for. Okay, so now now I want to just say a few words about something more speculative than this, which is something that I worked on and actually still a bit working on, which is could there be interacting ON models in some sense in D bigger than 4? So I'll be brief, but you can. So this paper with Fei and Jombi, in addition to review what goes on between 2 and 4 dimensions, it also contains some story about what goes on between 4 and 6 dimensions. And actually, it's an old thing about QFT that if you take this phi to the 4 theory with a negative coupling, then it's actually asymptotically free. This was actually, I think, Kurt Semantic pointed this out before the discovery of asymptotic freedom in non-abelian gauge theory, because there was basically, he was one of the very small number of people searching for asymptotic freedom. And this is related to the fact that if you formally take this beta function equation and push it to 4 plus epsilon equations, there is actually a UV fixed point at negative lambda. Okay, basically this equation here in 4 plus epsilon dimensions has a solution with negative small lambda. It's rather similar to what we have here, right? You basically have a UV attractive fixed point. So are we supposed to take it seriously? I mean, usually a theory with a negative coupling, you would think it's not stable, or it's at least metastable. So for whatever reasons, we started thinking about it, and we came up with a different way of describing this putative theory, if it exists. And this is So let me make a couple of observations about our large N results that I explained how they're obtained just from using this Hubbard-Stratonovich transformation. So we have this dimension delta phi, and let's look at it. Let's plot its leading 1 over n correction, this eta 1, as a function of d. Okay. So in a CFT, there is a notion of a unitarity bound. So for a scalar operator, there is the unitarity bound. Yeah, maybe I should write it down here. So this is the scaling dimension. Unitarity bound says that delta phi has to be greater than this d over 2 minus 1. Right? And you see that d over 2 minus 1 is the leading term in delta sub phi. So if eta 1 becomes negative, then you immediately know that the large N theory is not unitary. Right? If you plot this eta 1, well, it's 0 in 4 dimensions. This is not surprising. And it's 0 in 2 dimensions for reasons that I explained already, because these two theories become very, very weakly coupled. But then this is the famous positive Wilson-Fisher region, which people have very much under control now. But then, interestingly, it's positive between 4 and 6 before it goes negative above 6 dimensions. So what about this range between 4 and 6 dimensions? Could there be some sensible theory? I should say that this contradicts what people in some sense say in all the textbooks, because in all the textbooks they say that already the theory in 4 dimensions is trivial, and above 4 dimensions there cannot be an honest fixed point. I will explain why what we're saying is probably not in contradiction with these rigorous results. And but let us first try to see if we can define this theory better, because if you define this theory via this phi to the 4 interaction, then the interaction term is irrelevant. So that theory is not renormalizable. So that's, strictly speaking, not allowed. So can we write down a renormalizable field theory, for example, below 6 dimensions, which will have ON invariance and will agree with some of these results? And that I think we did. The whole point is that this theory must have cubic potential. This is like the weird part about this theory. Right? Normally we don't like cubic potentials because they're unstable. But we can nevertheless, if you read any field theory textbook, especially Srednitsky's textbook is entirely devoted to phi cube theory in 6 dimensions. You can formally do perturbation theory in phi cube near 6 dimensions. And we just looked at a model with ON, the minimal interaction in 6 dimensions, which is renormalizable and has ON symmetry. So it has n fields phi I. It has an additional sigma field, and then these 2 coupling constants. Sigma, the one for the term sigma phi I, and the other one for sigma cube. If you will, it's a little bit like a bosonic version of Yukawa coupling. Right? It's something, and I'll say a bit more about this later. Now, when we started talking about it at first, I could not believe that someone didn't compute this beta function somewhere, because this is really stuff from before I entered the field. We couldn't find it, but then it turned out that somebody, maybe Ma, one of these actually did compute the one-loop beta functions. And John Gracie, who then started working on this, I think he has a reference. But It's not important. I mean, he did it just purely in 6 dimensions, while we wanted to develop 6 minus epsilon expansion, and that nobody did. Then these are the 2 coupled beta function equations. And it's not that hard to develop both the large n and finite n search for fixed points. And the nice thing is that at large n, there are IR stable fixed points at real couplings. I should say that this theory was explored a lot by the great Michael Fisher of Wilson Fisher. But he just took only the theory of one field sigma. And then you'll see that there is a fixed IR stable fixed point, but at imaginary coupling. And this theory actually is perfectly OK, and it describes something that people see in statistical mechanics called the Yang-Lee edge singularity of the Ising models. But anyway, so people have played with these things, but this I think was not noticed, that for large enough n, and I'll say exactly how large. At one loop, n has to be bigger than 1038. Can you believe this? But above that, there actually is a fixed point. And these are these fixed points, for example, for n equal to 2000, you see them, the 2 with red dots. But what happens when n goes below 1039, these 2 beta function curves no longer cross. And then these fixed points become complex. Now, lately, there has been a lot of interest in such complex fixed points. I'm not totally sure why. Maybe people have run out of real fixed points. But there is actually one buzzword that if you Google it, there is something that people call complex CFT. Complex CFT. Of course, lots of complex fixed points are known, because generically, if you write some beta function equations, and they can have complex solutions. There were papers by this title by Zahn, Garbenka, Rychkov, and collaborators. But the phenomenon is rather ubiquitous, and this is, for example, one simple model where there are complex fixed points. I'll say a bit about their physical interpretation, but actually they have some interesting interpretation just when these 2 touch, then or nearly touching, then it's OK. So let's look at, for example, the dimension. So then we did actually a 3-loop calculation, and Gracie did the 4-loop calculation. Yes?
So this is for these 6 minus epsilon, right?
Yeah. The idea is basically you compute. You have to compute 6-dimensional beta functions. These are the leading 1-loop beta functions. Then you can consider higher corrections. And in 6 minus epsilon, you just have to add these terms here, over epsilon. These terms are present there for trivial reasons, because just to make the coupling dimensionless, you have to add some power of scale. And then when you differentiate you add some mu to the epsilon over 2. And then these shifts come out. Right, so this is similar to what I was doing in 4 minus epsilon for the established 5-4 theory. Yeah.
And did you say what was the motivation for going to this dimension?
Well, the motivation was the following. Let me say it again. That when you take this is also an established formula obtained many years ago. I think first in the 70s. You basically compute the leading 1/n scaling corrections, 1/n corrections to scaling dimensions. And you see where could possibly do we have a nice theory, okay? The motivation is that in this range between 4 and 6, this is positive. So the theory looks okay. So the motivation actually comes from 1/n expansion for this theory. but pushing this 1 over n expansion above the traditional 4-dimensional boundary.
Maybe there's something I don't get, but so is there any system that can be described by these dimensions? Or is it kind of, I don't know, do you maybe just get some theoretical insight into this?
Yeah, I think it gives you some. Well, first of all, these ON models are completely classic. If you can say something new about ON model, you're already somewhat in business. Right? And I think we did, actually. In principle, you can simulate this on a lattice. If you have a very powerful computer, you can. I'll actually Bootstrap people very much connected with this. And for example, they found in D = 5, they found what looks like a nice island for ON model with n = 500. They can easily do any n you assign to them. I mean, think about it as the space of exploring the space of possible scalar field theories with ON invariance, and just see where this quest leads you to. Or yes.
Just a general question about when you deal with field theories which do not have asymptotic freedom. So when you have a non-trivial UV fixed point, so
no, but that's the whole point. We found another theory where it's an IR fix. It's an IR stable fixed point. See, we replaced a non-renormalizable theory by a renormalizable theory with the same symmetries. Let me show this again. Yeah, these red dots are actually IR stable fixed point. That's why it even says IR. In this cubic theory, if you study these equations, they're perfectly IR stable fixed points. Yeah, if you don't worry about the behavior of the sigma cube potential at large sigma, these theories are completely renormalizable. That's why we can do this. Yeah, that's basically was the main point of our paper. That okay, so now so what do we make of these theories? Here is a bit of history. For example, for n = 0, Michael Fisher in 1978 developed 6 minus epsilon equation at imaginary coupling, but that was a manifestly non-unitary theory. And the dimension of the sigma in that theory violated a unitarity bound. Believe it or not, there are actual lattice systems that exactly agree with that theory. If you are on a Euclidean lattice, you can violate unitarity bounds without any problems, and these theories actually make perfect sense. Okay, but here is the main catch, and this is what we're finally trying to write a paper about. It's something we knew already years ago, but somehow got distracted. You actually don't expect this theory to be completely stable. This is obvious, right, because of the cubic potential running away. But nevertheless, there are arguments that it's metastable. Basically, if you study this theory on a sphere or study it on a cylinder, there will be some curvature that adds a quadratic term to sigma. That's the standard thing, that there are curvature couplings. Like there will be curvature coupling like r sigma squared that appears, that's so-called improvement term from the improvement term, which is necessary to make has anyone heard about a paper called the New Improved Stress Energy Tensor? Yeah, Jakiv, Kallan, and Coleman. Kallan, Coleman, Jakiv, right? That's an amazing early paper. They basically pointed out that if you just take a free field and say 4 dimensions, right? if you want this free field to define a conformally invariant theory, you need to add a special improvement term like this. Without it, it's not conformally invariant. So basically, when you put it on a cylinder, then there will be such a sigma squared term. Then your potential is not purely sigma cubed. It actually starts looking like this, kind of. And you can be expanding here. And then the instability is actually non-perturbative. It's a tunneling instability. So it's tunneling. So the theory is actually metastable, and we basically showed that there will be imaginary parts of scaling dimensions, but they're exponentially small, of order e to the minus an over epsilon, or even in d equal 5, they're of order e to the minus n. And if you are trying to solve this theory on a computer, and you see an imaginary part which is like 10 to the minus 100, you will obviously never notice it, right? So this theory can be made very long-lived at large n. And I think this is the way in which this does not contradict all the rigorous theorems. The rigorous theorems don't address theories like this, which are metastable but very long-lived. And actually, Zhijin Li and Ning Su a couple years ago studied the d equal 5 version of Bootstrap for n equal 500, and they found very nice, well-defined islands, which presumably, and they agree very well with the 1 over n expansion. So the bottom line is that there may be still something unexpected even in these ON models. If you go to higher dimensions, if you allow this very slight metastability for them and so on. But hopefully we will come out with this paper. I mean, we basically study some instantons and for these theories. And okay, any questions?
Yeah, sorry.
Mm-hmm.
I'm a bit confused about the fact that you were mentioning that the fixed points should be there just for n larger than 1038.
Yeah, otherwise they become perturbatively complex.
Yeah, but here you have n equal 500, so...
Oh, yeah, that was only in 6 minus epsilon.
Okay.
Yeah, in 6 minus epsilon, it's very well defined that you have to be at least 1040. But as you go down, there were actually, so this is what these higher loop calculations allow you to do. They allow you to estimate how n critical varies with d. And there was definitely some reduction to smaller numbers near d equal 5. D equal 5 is the most interesting case, you know. So it's not surprising that it's below. But the main thing is to improve on this bootstrap. I mean, I think this was only a preliminary, like one bootstrap study, but more questions? Okay, so I hope I convinced you that there is some interesting stuff you can learn from large n expansions, right? Because you would never think about a theory with 1048 or 1040 fields if you weren't a large n person. Okay, so now let me talk a little bit about similar fermionic models. For them, actually, there is pretty strong motivation. I think Misha discussed them also. And these theories are often a bit closer to what condensed matter people want to study, for example. So there are basically two classic examples. One is called the Gauss-Neveu CFT. David Gauss and André Neveu wrote this classic paper about large n theory in 2 dimensions. And I'll talk about this. I will not talk about conformal QED, even though this is like a very sort of active topic now, but I just don't have time to talk about it. You can ask me if you want. But so the Gauss-Neveu model, a classic paper where they studied this model in 2 dimensions and found behavior very similar to this nonlinear sigma model. Namely, they found asymptotic freedom in this fermionic model. So if you take d equal 2, right, the scaling dimension of psi is what? 1/2, right? So psi bar psi squared term has dimension 2, it's marginal. And you can calculate the beta function, and it has a negative sign. So this was one of the early examples of asymptotically free series, albeit not in 4 dimensions. But and the people were excited about it because it exhibits like some symmetry break, some dynamical symmetry breaking. There is a nice large N solution of the model. I already talked about this nonlinear sigma model. But then the question is, what if you try to push this Gauss-Neveu model above 2 dimensions, right? Then you immediately face the same problem that Harvey was just asking about. It's the interaction is not renormalizable. It's similar to what we did in 5-4 theory with above 4 dimensions. So you need some kind of reformulation of this theory. And let me exhibit what's the right reformulation of this theory. Well, let me first say that there is a 2 plus epsilon expansion, which was also developed early on by people. Very similar structure, actually, to the nonlinear sigma model. Again, this n minus 2 shows up somehow. N is the number of components of Dirac fermions. But usually people are wary of these non-renormalizable UV fixed points and so on. But there is a similar trick to what I just showed you with this cubic Yukawa type interaction, which is, and this was introduced by 2 groups. One was Zinjustan, a group of 1, and Hasenfratz, Janssen, and Kuti. And these papers, I think, were inspired by actually some activity on the Higgs in the early 90s. So they were actually motivated by phenomenology, I think. But basically and the Zinjustan paper I particularly find clear, and he called it the Gauss-Neveu Yukawa model. He basically reformulated this model as a Yukawa model with 1 real scalar sigma and n fermions psi, n flavors of fermions. And then in 4 dimensions, you also have another marginal term, which is sigma to the 4. Right, so now this is completely stable. You do the 4 minus epsilon expansion in this model is perfectly well defined, and you find that G2 star is positive. Like you have a positive stable Lagrangian. And this, without a doubt, describes continuation of the Gauss-Neveu model above 2 dimensions. So again, even though this idea of UV fixed point is not reliable, it turns out to be correct in this case. But this is a fully UV complete description of this theory. And just notice the similarity between this and this RN theory that we were proposing in between 4 and 6 dimensions, right? It's very similar, right? We also introduce this extra field sigma, and then instead of psi bar psi, we had phi I. So it's a bit like Yukawa theory with scalars or something like that. And here it's, as I said, it's if you don't like unstable theories, you will immediately stop. But I think in the end, it's actually can be very, very stable. But this theory is manifestly stable, this GNY model. And has anyone here heard the term GNY model? No one. Well, these bootstrap people talk a lot about GNY model.
So in which sense the GNY model is the extension above 2 dimensions of this original Gauss-Neveu model? So if you don't have a kinetic term for the sigma and the sigma to the 4.
Yeah, I think it's in I think in the sense that I'll show you in a second. So if you take this model, you can again develop large N expansion even above 2 dimensions using this extra sigma field. Right. And then you can check that this GNY model has 1/n expansion which agrees with that. But that model also makes sense for any finite n. So it's a kind of redefinition. It's a proper you can think of the GN model is OK in 2 dimensions, but it's just not OK technically above 2 dimensions. You have to replace it by another theory. And that another theory is GNY model. That I'm very everyone will agree to this statement, I think. So, and in particular, it's UV complete, it's renormalizable. You can push this 4 minus epsilon equation. Then you can then also use the 2 plus epsilon equation from the non-renormalizable theory in the same spirit as we did for the ON model and define the theory in the whole range between 2 and 4 dimensions. And now the 1/n expansion, that's something that Gauss and Neveu always believed in and wanted to do. It's completely analogous. You can, again, for any theory with this sort of double trace interaction like O squared, you can introduce this sigma field, then do exactly the same thing that I already showed you where O was phi squared operator, derive the induced effective action here, right? And then use it to compute the 1/n corrections in exactly the same way. And this was done already in the 90s. The people did this, I think, started in the 80s and did it in the 90s. So you get these perfectly well-defined 1/n results. And you can compute similarly these, for example, delta psi. And this 1/n result agrees with the 2 epsilon expansions. Okay, it agrees with the 4 minus epsilon and with the 2 plus epsilon expansion. So it's like a little set of tricks that you can use to cross-check all these different methods. And now the Bootstrap people are also working hard on these fermionic models, because fermionic models are of much interest actually to condensed matter community. Like for example, some materials in 2 spatial dimensions and time may well be described by these type of 3-dimensional fixed points. So there is a lot of interest, and I think they obtain results that are in agreement with all these methods. Okay, so I think I'm gonna I spent way longer than I expected on vectorial theories, but maybe it's good because it's like a very classic stuff in a way. So now I want to switch gears but maybe before I switch gears to that Hooft large N limit, I want to just comment a little bit about. So these vectorial theories, you saw that they're basically the 1/n expansion is analytically doable in any D, and why is that? Basically, so why are these series so doable? And this is because a very small set of diagrams contribute, survive in this vectorial large N limit. So this. So in this vectorial large N, and it's you know, like if you, for example, draw the vacuum diagrams of the theory, like the first one, like let's just take some 5-4 theory with some arbitrary set of fields, not just one field, but so you can have some generalized 5-4 theory with interactions like Ci, j, k, l, phi I, phi j, phi k, phi l. and this index can range over some huge number of values or something. And then you start, so then in the vectorial case, theCijkl is very special, right? TheCijkl, so for just ON symmetry, you basically have thatCijkl is equal to delta ij, delta kl, plus permutations. And then you get that the interaction then becomes just phi squared squared. Okay, but in this generalized theory, you can draw like all kinds of diagrams, right? Like this is the figure 8 diagram. Then there is something that we now call melon diagram. And then there will be like some stuff like this. And then you can even further draw some, then it explodes very rapidly. But here, you basically, everything is dominated by a very small subclass of diagrams called cactus. I think there are various colorful names, but one of them is cactus diagrams, where basically you just grow these things only in this way. Okay, so there are only, so each of these is just a 5-4 vertex. Okay, now this one is called a melon, and a melon is not a cactus, right? So, yeah, there are theories that are called now melonic theories, which are kind of orthogonal to these ones. Like for the melonic theories, these are subdominant, but for these vectorial theories, these are dominant. And you can, so if you read my notes, it's explained in detail how these things basically work out. Because if you look at, for example, the contribution of this vacuum diagram, it has 1 power of g. So this diagram scales like g n plus 2. And this one scales like g squared n plus 2. Okay, and this one scales like g squared, I think n plus 2 squared, something like this. Sorry, n plus 2 squared n. So you see that just from these simple, and you can look at the detailed notes where this calculation is done, the one that I wrote down at the beginning of my lectures. You see that when you send this, take the limit where g n is fixed, when n goes to infinity, then this gives a contribution of order n, right? So let's call this lambda, right? So this is just lambda n. This just gives lambda, and this is lambda squared n. And you expect the n, the overall factor of n, to be there because there are n degrees of freedom, right? So in these series, if you compute the sum over all diagrams, over all connected diagrams log z, you expect to see n times some function of lambda. And this function of lambda entirely comes from these diagrams, from these cactus diagrams. And you can think of these diagrams as basically exchanges of this sigma field. Like you have some contracted sigma fields here, and but this is just a fact, so it's a very simple and solvable sort of situation. Okay, and the index structure of the interaction here, if you think about this quartic vertex, it basically looks like this. Like, so this vertex is phi I, and then you have phi j, right? So there are two contracted I indices and two contracted j indices. So you can do very simple counting. You can then redraw these diagrams using this sort of notation with indices, and you see that each independent index loop gives you a factor of n. So for example, if you take this the leading one, right, this diagram can just be then redrawn like this. Like you have so this gives you two loops here, and each one gives n, right? So each index loop gives n. Loop that's summed over contributes n. This is the 0th order rule of doing large n series. Just redraw them with these index loops and count how many loops there are. But then, for example, if you redraw like this one, you see that you indeed you have something like this and then something like this. So there are still only two loops. So this is indeed g squared n squared. And here you'll find three loops and so on. So this rule basically works okay. So now I think I really do want to be finished with these vectorial theories. So now let me move on to matrix large n limit, or the 't Hooft limit. And this is a whole new topic, which is much more, in some sense, maybe familiar to you. Like, in fact, Graham was mentioning large n QCD and so on. So these type of large n limits existed for spin systems even before 't Hooft, but I think he made large n limits much more popular and so on. So let me talk about QCD, or just, let's say, SUN gauge theory. 't Hooft limit for SUN gauge theories. Or SUN gauge theory. So you all know what the Lagrangian for SUN gauge theory is, right? We just have, so we have a minus, so S is equal to -1 over 2g n mil squared, integral d dx, trace f mu nu. Actually, let me put this g inside f mu nu squared. Right, and f mu nu is the non-abelian field strength, right? It's d mu a nu minus d nu a mu plus I times g Young Mills commutator a mu a nu, right? Okay, so now, so basically these are just, for now I'm just discussing the pure glue theory, but this is already where this Hooft large n limit comes in, right? And you know that each of the gluon fields, so there are these couplings like this with the g Young Mills, and then there is a quartic coupling, right, with g Young Mills squared. Okay, so now, obviously we know that this theory is, by now there is, even though there is no rigorous proof, everyone knows that this theory is confining in 4 dimensions and 3 dimensions. And I will exhibit even some numerical results. But when this theory became formulated and accepted in 1972, 1973, as the right theory of strong interactions, there was tremendous activity trying to understand it. Actually, since Gell-Mann recently passed away, there was this historic paper by Gell-Mann, Fritzsch, and Leutwiler, which was called something like the case for the color octet gluon. Like now everyone knows that gluons are color octet, right? But apparently in those days there were models with singlet gluons or something like that. And basically, apparently after they wrote this paper, this was already somewhere right after the papers deriving asymptotic freedom of strong interactions, but they basically, in just a few pages, said, this is it, this is the right theory. And then the floodgates opened, like people started really working on the theory, and they pretty quickly discovered that because the theory is asymptotically free, it's very hard to solve in the infrared, and people are still trying to solve it in the infrared, and it's very hard. I mean, now, of course, we know from the lattice much more, but then... And then 't Hooft came with this idea, like, people realized that there is no expansion, no small expansion parameter. And 't Hooft proposed to replace the SU3 color by SUN color. That was 't Hooft's legendary paper. Just in case you have doubts about large n, if you go on 't Hooft's list of publications, and he won a Nobel Prize for papers on renormalizing the standard model and stuff like this. His highest cited paper is this paper on large n. So even though this has not been rewarded directly by any prize that I know of, but it's an extremely influential idea. And basically, so he said, let's imagine taking the large n limit and in a specific way, which I'll describe. It's very simple to see. It's rather similar to what we saw there. And here is how, and he invented the so-called double line notation, right? The idea is to restore the indices for the gluons. So there will be one upper and one lower index. So each, right? And this will also be like this. And the index structure of these interactions is basically so you represent this upper index with you think of these two indices separately, and it helps actually to forget that there is a tracelessness constraint. You can just work with UN instead of SUN. So the propagator for Aij, for example, if you look at Aij with A prime, I prime, J prime, right? The leading index structure will have the form delta Ij prime, delta J I prime J, and then some 1 over n correction, which I won't even care, plus order 1 over n. And there is a way to pictorially represent this. You basically replace this single wiggly line by a double index line, where you have Ij by this double line, where the upper index runs, one index runs this way and the other index runs this way. And this is called the 't Hooft double line notation. Double line notation. Okay, and then we can try to sketch what these different interactions look like in in this double line notation. Okay, so in particular this one, if you strip away there is a very big simplification that you can do if you just want to keep track of these n dependencies, which is instead of this interaction, this cubic interaction trace, it really comes from trace d mu a nu minus d nu a mu, then a mu commutator a nu, and then you have IG here. You can just boldly replace this by just trace phi cube. Like phi doesn't have these space-time indices, but it's an adjoint field of the SUN. So phi is the phi is a Hermitian matrix, right? Generator of SUN. Hermitian traceless matrix, but the tracelessness can be ignored because it's a difference between SUN and UN, which disappears in the large N limit, right? Then you see that this can just be written as phi. This is just phi ij, phi jk, phi ki. Right, so this can be rewritten in this double line notation like this. Right, so you have here, for example, this is the I index, this is the J index, and this is the K index, and you can attach orientation too. So you get like an orientable graph because each of these strands is basically has an orientation. Okay, so and then similarly there is, as an exercise, you can also write down. So you can also write down this one. For example, this is a water G Young-Mills squared, and this can be just written as this one with some specific orientations. So now let's do a very simple estimate, which is, so we learned from this vectorial large N limit that as n is sent to infinity, G has to be somehow sent to 0 to compensate for the large, and you have to keep some combination fixed. So let's do a correction to the gluon propagator, just one loop gluon propagator correction. Right, which just looks like this. It's a familiar graph that contributes to the beta function. And then we can see, so this obviously carries a factor of G Young-Mills twice. And what factor of n does this carry? And this is where this double line notation comes in very handy. If you redraw it, you get the following structure. And then there is the maximal graph is where you also have this free loop, right? So then you have this type of situation. And then this index here, this is say ij, and this is some index k that can take any value. So because of that, since it can take any value, there are n separate contributions to this graph. So this graph is therefore of order G Young-Mills squared n. It's of order G Young-Mills squared n, and compared to the free propagator, which is just of order 1. so this clearly, you don't want this to diverge. So you want to keep this fixed as in the large n limit. And this is actually often called lambda. And this is called the 't Hooft coupling. The 't Hooft coupling. Right. So then there is a very big sort of result, which maybe I'll flash a few slides on this, but essentially you can start playing with some further graphs along the same lines, and you find. So what's the simple next correction that you can have? You can, for example, do a more complicated graph where you add say this internal line here, right? This is going to look like, so now you will have here you will have here two free index loops. Do you see why? Because basically this propagator here is a double line, and you maintain this structure of the vertex, and here you now have two disconnected loops, like say K and L. Right? Agreed? So now let's look at what the order of this graph is, right? So this graph now will be G Young-Mills now to the 4, right? Because there is 1, 2, 3, 4 couplings, and then there are two separate loops. So this is n squared. Right, so this is lambda squared. So this graph still has to be included, right? It's when lambda is of order 1, these two graphs, this one is not suppressed by 1 over n compared to the previous graph that we had. And then you can, I suggest you play with this in the evening. It's a lot of fun to play with different graphs. The school is ending soon. It's one of the last chances to. So, for example, you can do the same thing. You can start adding all these lines here. And then you will basically discover that anything that can drawn in a planar fashion is still surviving, is still not suppressed. So, and I'll show why this is in general at the beginning of the next lecture. But with the moment the graph cannot be drawn in a planar way, you immediately get suppression by 1 over n squared. Okay, so let's just see why this. So let me exhibit this first non-planar type of graph. Well, okay, so this is the graph that looks like this. And this gluon line goes underneath this gluon line, right? So this is a graph of order G Young-Mills to the 6, right? Because there's 1, 2, 3, 4, 5, 6 coupling. And we want to figure out n to what power that we put in here. Okay, so now we have to translate this graph into a double line notation. And let me draw how this looks. So you will have like this one. This is sort of the outer part of the graph. And then Okay, so here we have okay, maybe I should write. So you see that each structure of the vertex is exactly as we need it here, right? But then you can traverse this this internal loop, and you see that this is really just one loop, right? There are no two separate or three separate index loops. If you follow with your finger, you basically just come back to one point. So there is just a single index loop inside, not two like we had there, right? So this is just single index loop. And therefore, this just gives me a power of n here, right? And this is nothing but lambda cubed divided by n squared. Okay, so you see that the non-planarity, so the leading non-planar graphs are already suppressed by 1 over n squared compared to planar graphs. Okay, so and then we can the simplest is to show how this works for vacuum graphs. Like if you just sort of look at so if you draw vacuum graphs, where we just have log z, and then you see that, for example, any planar graph like this one, for example, or anything here, that contributes n squared. But a graph where we insert non-planarity, where one gluon line passes under another one, that's of order n to the 0. And when there are two such things, there will be n minus 2. And what Hopf realized is that there is a topological classification to these graphs. Like these graphs have topology of a sphere, two-dimensional sphere. These graphs have topology of two-dimensional torus. These have, so this is topologically a spherical topology. Topology of sphere. And this is torus, and this is a sphere. Torus is like a sphere with a handle, right? So genus is the number of handles attached to the sphere. So this will be genus 1. So this is so-called genus 1. If you just think about smooth surfaces, a sphere looks like this. And then the torus, you can draw sort of like this. But you can think of it as a sphere with an extra handle attached. So this is g equals 0. This is g equal 1. G equal 1. And this will be g equal 2, and so on. So essentially, you can simply prove that the...
How do the g equal 2 diagrams look like? So the g equal 1 is just where the lines like cross each other?
Yeah, you need two of these crossings, basically.
So only has one crossing?
Yeah, this one has only... So if you want two crossings,
so the crossing determine the number of genus?
Yeah, this is one, then this is another one. So there is another defect like this. Yeah, and each one, like, you can't draw it on a planar way, but you can have a handle that passes sort of one index under another. And yeah, so in general, the weight, and then there is the so-called Euler theorem, which says that the Euler characteristic, so the Euler characteristic chi is just equal to 2 minus 2g. And one can show that the weight of the graph, so each graph is weighted by n to the chi, right? N to the chi, which is n to the 2 minus 2g. And this is consistent with what I'll give a very simple general argument next time. It's actually in my notes also, but you see that all the spherical topology genus 0 go like n squared, and genus 1 goes like n to the 0, and so on. And this is also why string theory people like large n theories so much, because these, you can think of these as kind of string world sheets. Like these diagrams define sort of world sheets swept out by an extended string-like object. Okay, so maybe I should stop for questions, because I can continue next time. Questions?
Let me ask now, since you mentioned the string theory and I'm going in completely naive, so do the closed string amplitudes correspond to the planar diagrams in some sense? I mean, at the level of the topology, or?
Yeah, certainly at the level of the topology they do, because in fact there is a very close connection between glue balls and closed strings. Right, and one thing that I will mention next time is that, so one outcome of 't Hooft's investigation was that this, say, pure glue SUN theory, so SUN pure glue is a theory of weakly coupled glue balls, which interact with strength 1 over n, which interact with strength 1 over n. Okay, so a glue ball is like a ring of glue, if you want. It's like a flux line, and this. So that's where this whole dream of QCD string comes from. It becomes much nicer in the large n limit, because you basically have one glue ball and another glue ball. They can join and form a third glue ball. And this joining strength is of order 1 over n. So you have like one closed string, another closed string. They can touch and form a string with amplitude 1 over n. So by taking large n limit, you see that these glue balls will be essentially almost stable. They barely decay. And you can consider this whole perturbation theory in 1 over n for the interactions. And there are, of course, lots of, for example, one model where things work very explicitly is there are two-dimensional models, like 't Hooft model in 1+1 dimension, where you get meson, you get like a theory of, very simple theory of mesons. Mesons appear after you add flavors, and so mesons are like closed strings, open strings. They have endpoints which are quark and anti-quark, like this. So there is a very big parallel between string theory and large n QCD. And this is actually how string theory was born, by studying these things. So in the context of ADS-CFT correspondence, you have much closer connection than in. But I think I'll try to talk about this tomorrow. Yeah.
So we can actually put fermions in this model as well?
Oh, absolutely. Yeah, the fermions actually are there. They're just quarks, right? So if you add to the Lagrangian, so you have this S is minus 1/2 trace F mu nu squared, right? And then you will have I psi bar d mu psi, right? Where d mu is just the covariant derivative plus I g a mu. So literally what you read for QCD Lagrangian in any textbook, and this. So, and there will be some flavor index. Let's call it I, or big I here. So there will be some number of these flavors of Dirac fermions. These are just the light quark fields, and they create endpoints of these flux. So you have like a quark creating some chromoelectric flux line that ends on the anti-quark. And this vibrating bound state looks like an open string. I wasn't planning to talk so much about this aspect, but you see, like, that's basically how string theory was initially invented, from studying mesons and things like that. Mm-hmm.
Is there a hope that maybe the Lagrangian theory will be solved?
Well, I think this hope has existed ever since Toft's paper. I think there's definitely something very concrete. So the theory that was solved was the supersymmetric version of this theory, namely the n=4 super Young-Mills theory. So in that sense, right. But there are versions of those models which are confining. The interesting thing is that it's not absolutely necessary to have a confining theory to have a dual string description. That's what we learned. Like, you can just have some singlet operators and see how they interact. Yeah, like, for example, the Wilson loop can be computed in a conformal. But there are also confining theories, like the one that Tressler and I, for example, formulated. They still have a dual gravitational description. So I think that there has definitely been a lot of huge amounts of work. There has been some progress. I think the dual of just, say, pure glue QCD continues to be like a really amazingly hard problem. But the fact that we understand like some duals of some large N theories exactly, that's already huge progress. Yeah. And all the large N counting rules apply to those theories as well. Okay, so I'll try to explain some of that tomorrow. Then, yeah. Thank you.